Welcome to The Explainer, everyone. I'm absolutely thrilled to have you here today. We're going to unlock something truly fascinating. For those of us who love data and logic, combinatorial analysis is kind of like this beautiful engine running right beneath the surface. It's the mathematical backbone of, well, almost everything, from complex computer science algorithms and cryptography, all the way to the foundational laws of probability that literally govern our universe. Today, we're going to break down the exact mathematical principles that dictate how we count, group, and arrange the stuff around us. It's going to be a super exciting, insightful journey into the actual mechanics of choice. So let's just get right into it. Okay, this right here. This is the single, absolutely foundational question that dictates the entire mathematical landscape we're about to explore together. Does order matter? Really think about it for a second. If you're punching a pin into your phone, 1, 2, 3, 4 is obviously very different from 4, 3, 2, 1, right? The order is everything. But if you're tossing ingredients into a blender to make a smoothie, strawberries then bananas gives you the exact same outcome as bananas then strawberries. The order is entirely irrelevant. And that simple real-world distinction is the beating heart of combinatorial analysis. Honestly, just think about how much computing power is saved or spent based purely on the answer to this one single question. It literally dictates whether an algorithm finishes in milliseconds or takes millennia.
Section 1. The rule of order and defining the two paths.
Okay, let's dive into this and look at how every single counting problem splits down two distinct paths. First up, consider permutations. This is the path where order absolutely matters. This is your PIN code, your locker dial, or maybe that highly specific seating arrangement at a fancy formal dinner. Position is key here. Every single shift in position creates a uniquely counted state. Now contrast that directly with combinations. Over here, order doesn't matter at all. This is your smoothie, or it's picking a team of 3 people from a group of 10. It doesn't matter who's picked first, second, or third, they're all on the exact same team at the end of the day. These are our two foundational concepts pitted strictly against each other as a kind of mathematical duality.
Section 2. Permutations, where order matters.
Let's transition our focus directly into the specific mathematics of permutations. This is where the sequence of every single element is fiercely protected. So here's the formal equation for permutations without repetition. P of n comma r equals n factorial divided by the quantity n minus r factorial. Now we use n factorial to calculate the total possible sequences, but the real magic, that happens down in the denominator. Dividing by n minus r factorial mathematically shears off all those alternate realities we just don't care about. Imagine an Olympic race with 8 runners, but we only care about the gold, silver, and bronze medalists. The total pool is 8, that's our n, but we're only choosing 3, that's our r. We really don't need to calculate the arrangements of the 5 runners who didn't medal, right? So the denominator perfectly slices away those irrelevant permutations, leaving us with precisely the number of unique, ordered outcomes.
Moving right along to Section 3, combinations, where order is ignored.
Now, what's really interesting about this slide is the combination formula itself. Look at C of nr. It looks incredibly similar to our previous formula, doesn't it? The numerator is still n factorial, and the denominator still has that n minus r factorial. But look closely at the brackets. There's an absolutely crucial introduction here, an extra r factorial sitting right there in the denominator. That single addition changes the whole shebang. Why? Well, because when order doesn't matter, our previous permutation formula actually overcounts. It counts A, B, C, and CBA as 2 entirely different things. But in a combination, a group is just a group. By dividing by r factorial, which represents the number of ways to arrange the items we just picked, we're mathematically wiping away all those identical groupings. We basically collapse all the overlapping variations back into a single pure choice. Let's visually connect this transformation, because honestly, it is wonderfully elegant. Step 1, you start with your permutation. You're counting up all the possible arrangements where order matters. Step 2, you divide out the redundant orders using r factorial. You are quite literally stripping away the importance of position. And then, step 3, you seamlessly arrive at your combination. A combination is really just a permutation that's been perfectly disciplined to ignore order. To put it simply, permutations give you every possible string, and combinations group those strings into meaningful bundles.
Section 4. The repetition twist, altering the mathematical landscape.
So, just when you think you've got a perfect handle on this whole universe of combinations and permutations, the math throws a massive plot twist at us. Up until this point, we've been operating under standard rules, right? Once you pick an item, it's removed from the jar. It's completely gone from the pool. But what if we allow you to reach in, pick an item, and then replace it? What if you can pick the exact same item over and over again? This completely shatters our previous assumptions and requires a totally new set of mathematical calculations.
Let's look at permutations first, but this time with repetition allowed. The formula drastically alters, and honestly, it beautifully simplifies. It just becomes n to the power of r. Think about a standard combination lock, which, ironically, as we now know, should actually be called a permutation lock. If you have 10 numbers to choose from for your first dial, and you can repeat numbers, well, you still have 10 choices for the second dial, and 10 choices for the third. It's literally just 10 times 10 times 10. The total pool, n, multiplied by itself for every choice, r, that you make. It's clean, it's logical, and it's incredibly powerful. In fact, this simple exponential equation is exactly why adding just one more character to a password makes it exponentially harder to crack.
Let's move to and see how this builds when we bring repetition into the world of combinations. Now, this is perhaps the most abstract formula we'll look at today. C of the quantity n plus r minus 1, comma r. Because order doesn't matter, but you can choose the same items multiple times, the math requires a pretty powerful conceptual leap. Think of it like walking into an ice cream shop. They have n flavors and you want r scoops in your bowl. You could get all chocolate or maybe a mix of vanilla and strawberry. To mathematically count every possible bowl, we use what's called the stars and bars method. You basically use mathematical dividers, or bars, to separate the distinct flavors you choose. That minus 1 in the formula, that represents those dividers. We're essentially choosing where to place our scoops and our dividers in a single row. We expand our total options by adding our choices and our dividers to ensure we capture every possible grouping without double counting the repeats. I know it's a bit heavy, but it is a profoundly elegant solution to a really complex problem. And this brilliantly illustrates our complete matrix. We've taken the dense, complex source text of combinatorial analysis and organized the whole thing into a single, highly satisfying visual framework. Across the top, you define your path based on the rule of order, and down the side, you define your rules based on repetition. Having this visual framework locked in your mind is incredibly powerful when you're approaching any kind of data logic. By answering just two simple questions, does order matter and can I repeat my choices, you instantly know which of these four foundational equations holds the exact answer to your problem.
So, the crucial point is this. Behind these four dense equations, behind all the factorials and the exponents, lies a beautifully simple conceptual logic. Combinatorial analysis isn't just about memorizing random letters and numbers. It's about understanding the very fabric of how things go together. Next time you look at a randomized playlist, a lottery ticket, or a complex search algorithm, I want you to ask yourself, is the universe strictly mandating the order, or is it just a combination waiting to be simplified? Keep looking for that underlying structure, and I'll see you in the next explainer.